Yeah. Are you seeing this? Okay, great. So this will be really the first of 2 lectures on Wannier functions in the solid state. The next one will be given tomorrow morning by David Vanderbilt. And as you probably all know, this is something that David and I started actually many years ago when I was a postdoctoral professional in Rutgers under the supervision of David. But in the course of the years, many people became involved in the project. First and foremost, Ivo Sousa, that at the time was a postdoctoral researcher, first with Richard Martin and then with David Vanderbilt, that was really the leading person for the so-called disentanglement developments. Ivo is now in San Sebastian in northern Spain. And then Arash Mostofi and Jonathan Yates became involved. Arash was a postdoc of mine at MIT, and Jonathan was a postdoc in Berkeley with Ivo. Now they are faculty members in Imperial College London and in University of Oxford, and they've really been the leading force in the last few years to really bring the code to a modern Fortran 9 implementation and to keep developing and supporting it. And to this effort, lately, Giovanni Pizzi, that is a postdoctoral researcher here at EPFL, has also started taking part. He contributed the thermoelectric module. And of course, David Vanderbilt is also always linked to the effort. There will be more people that I will mention at the end. I have to apologize. I've been battling a cough for the past few weeks, so sometimes I will have just to stop. If you want to learn more about the topic, probably the best place where to start is this long review article that we have written last year for Review of Modern Physics that has everything you wanted to know about the theory of Wannier functions. And I list also the website where you can download the code and all the tutorial material. And by the way, even if we might not have the Wannier 90 tutorial that you had hoped for, the code has excellent documentation and is quite self-explanatory. So it should be quite possible for some of you to sit down and install it on your own and try to run it as a post-processing either of VN2K or of PWSCF, that are some of the many codes that have been interfaced with it. So with this introduction, let me actually go into the basic description of the problem. Forgive me, the first 2 or 3 slides are really self-explanatory, but the framework that we are dealing with is that of solid-state physics. And we are always going to think at calculation done in periodic boundary conditions. That is, we define a unit cell and we replicate whatever is inside that unit cell an infinite amount of times according to the translational periodicity of the Bravais lattice. And as you know, in 3 dimensions, there are 14 Bravais lattices that I've briefly reported on the left. They are really defined by the 3 primitive lattice vectors A1, A2, and A3. So if you want to describe something as simple as, say, aluminum, that is an FCC metal, you choose the primitive face-centered cubic lattice, and you have just 1 atom in your unit cell, and periodically repeated, it gives you the entire crystal. You can use periodic boundary conditions also to study disordered systems, something like amorphous silicon or liquid water. They can be studied in periodic boundary condition, provided you choose a sufficiently large unit cell. You could take a simple cubic cell, throw in 50 water molecules, do an ab-initio molecular dynamics run to let them thermalize. And what you are going to describe is not infinite liquid water, it's something that is liquid-like and periodically repeated, but you will reach the thermodynamic limit of liquid water by increasing the size of your unit cell more rapidly if you were to describe a droplet of water, basically because in periodic boundary condition, you do not have any free surface. Your water molecules never see a water vacuum interface. So periodic boundary conditions can actually be used to study not only solids, but disordered systems, both solids and liquids. And you can even if it's not the best choice, study isolated molecules. That is, provided there is no overlap between the wave function, say, of your methane molecule in a simple cubic unit cell and the periodically repeated image, your methane molecule will behave as if it were alone in the universe. And so there is, even if there are infinite periodic copies, they don't interact with each other. And of course, if your molecule has a dipole or is charged, you need to be very careful because electrostatic interaction are relatively long-ranged, and so you need to be careful about studying the limit of large supercells. But in general, you can even study isolated molecules in periodic boundary conditions, and all the formulation of Wannier functions that you'll see actually works perfectly well also for molecules in periodic boundary condition, and I'll comment on that. The second concept after that of the direct lattice that you need to remember is the one of the reciprocal lattice, that is the dual of the direct lattice that is defined by this dual relation. If A1, A2, and A3 are my primitive lattice vectors defining the unit cell, all vectors whose scalar product with A1, A2, and A3 satisfy those relations above are said to be vectors of the reciprocal lattice. And actually a plane wave with a wave vector G has the property that has the same periodicity of the direct lattice. And so the reciprocal lattice is what we use to classify excitation, and I'll come to that in a moment when I introduce Bloch Theorem. And that's a question for Tanusri. I presume that the audience is all familiar with Bloch Theorem and this concept, but tell me if I should go more in depth in this. So I'm assuming a basic knowledge of solid state physics, correct? Okay. Okay, very good. So just again, as a reminder, just to be on the same footing for the notation, when we have a periodic Hamiltonian, and being a periodic really means that H, the Hamiltonian, commutes with the lattice translation, and so that operator T of R is a lattice translation. So when the Hamiltonian commutes with the lattice translation, because it's periodic, we can choose, or we have the freedom to choose a very useful form for the eigenvectors of that periodic Hamiltonian that we label psi with two quantum number, a continuous quantum number k and a discrete quantum number n, and we call n the band index and k the quasi-momentum. And even if the Hamiltonian H is periodic, the wave function psi is not periodic, but has a very special form, is equal to a periodic part that we'll always call u and k, modulated by a plane wave with wave vector k. So Bloch theorem tells us that the form of an eigenstate of a periodic Hamiltonian is in the form of a periodic function u times a plane wave. The two quantum numbers are the band index n and the wave vector k, and the wave vector k decides the modulation of the wave function. I'll show that in a moment, and I won't prove it, but there are very simple ways to prove this. And this is an example, say, for a one-dimensional crystal. Suppose that you have something, like a linear chain of atoms, And now what we are looking in red is at a band structure. That is, we are looking at the eigenvalues of those eigenvectors psi and k as a function of k. And one other sort of outcome of Bloch theorem is that the k that we need to consider are only the k that are contained in the first Brillouin zone, in the unit cell of the reciprocal lattice, that for a one-dimensional system where the direct lattice has a unit cell of length a, in reciprocal space goes from minus pi over a to pi over a. So that red line are the eigenvalues as a function of k for the first quantum number for n equal to 1. And if you imagine this being actually an atomic chain, it could be a hydrogen chain, spaced every atom by a length a, you should remember that in the limit in which the spacing between the atoms becomes very large, so the atoms do not interact with each other, that red line will become absolutely flat, and that will be your energy of the first atomic level. So it's always very useful to have this picture of a solid, in this case the periodic lattice, and expanding it, and remembering that a band structure, as you expand the solid isotropically and all the atoms stop interacting with each other, that band structure, however complex it was at the beginning, will become a set of flat horizontal lines corresponding each of them to one of the atomic levels. And in that case, in that expanded picture, your eigenstates can actually be thought now as atomic orbitals. And rather than using a nomenclature nk, as in Bloch theorem, you can start describing them with a Wannier nomenclature nr, where n, that used to be the band index, is just now the atomic orbital, and r, rather than being the quasi-momentum, is the lattice site where that atom is located. So in the expanded view, there is a very clear Wannier representation of quantum numbers where each orbital in your system is an atomic orbital with an integer label n and a lattice label r. In the case when this thing starts interacting, so you go towards the equilibrium lattice distance, those flat bands starts to become sinusoidal or cosinusoidal-like. This is a simple exercise in tight binding from the Ashcraft-Mermin to see to first-order flat bands becoming sines and cosines. And if we were to look now at the different eigenstates, at the different wave function for this band at different k, well, remember that those are going to be a periodic function modulated by a plane wave. And at different k's, I'm showing in green the plane wave. So when k is equal to 0, the plane wave is a constant. And as k becomes larger, you start to have a modulation that becomes progressively of shorter wavelength until you reach the zone boundary. And so that modulation in green changes the periodic function that you see very well in the left panel, that is the original un of 0 periodic, and then at k different from 0, you see that there is a periodic function that is modulated by the green function, and the total Bloch function is the curve that is described here in black. So this is the picture of a band structure that you should have in mind. In 3 dimensions, things becomes more complex, or at least they look more complex. These are the valence bands for silicon, say, on the left. Silicon has 2 atoms per unit cell. It's an FCC lattice with a basis of 2 atoms. There are 4 valence electrons per atom, so there are 8 valence electrons per unit cell. It's spin degenerate, so it gives rise to 4 spin degenerate band. But again, if we were to explode isotropically silicon, those 4 bands there in red would become 1 flat 3s band and 3 flat degenerate 3p bands. But instead, the system is interacting, so the bands are not flat. And actually, if you stay on group 4, but you just go down, you go from carbon, say, to silicon, to germanium, to lead, the band structure still remains fairly similar, and lead ends up being a metal just because you see those conduction band in red on the right panel starts to be below the top of the valence band, and so the system has become metallic, but somehow the electron physics is still very similar. Okay, and actually, these bands that look very complicated, and I'm plotting it for the case of silicon, are actually to a large extent just a parabola. So all that spaghetti black lines that I've drawn on the left are really just a parabola, but folded according to the symmetry of the FCC lattice. So a free electron would have an energy versus momentum dispersion that is given by the black lines. And you see that in silicon, actually, electrons are very, very similar to free electrons. Just at the zone boundary, you start having an opening of the gap, and really this is because the potential that comes from the periodic array of the ions counteracts the electron-electron interaction, and the effective interaction is just a very weak perturbation of free electrons. So this is, again, one of those fundamental statements of band structure that Marvin Cohen was able to exploit in the late 60s when he developed empirical pseudopotential. You can actually reproduce perfectly the experimental band structure of silicon, both the valence and the conduction, just by perturbing a free electron gas with very weak periodic terms, and you just need typically 3 numbers, that is the 3 components that corresponds to the longer wavelengths of the reciprocal lattice to actually reproduce the band structure. Okay, with this introduction on band structure, let me go towards the Wannier representation. Tanusi, is this the right speed? Am I going too slow or fast? How is the audio?
For a minute. Is the speed okay? You all are following? Do you have any question? This is very basic, but do you have any question? So Nicola, there is no question and everything is fine, so you can move on.
Great. Okay, so we have discussed up to now the Wannier representation, and now, sorry, the Bloch representation. And in the presence of a periodic Hamiltonian, a periodic potential, we write the eigenstates in red. And now what I want to discuss is performing a unitary transformation. You probably remember that quantum mechanics, it's a little bit like classical mechanics. So in classical mechanics, you describe the dynamics of particle in 3-dimensional Cartesian space, but you can perform orthogonal transformation of your basis, of your reference system, and you can describe, say, a jet that was going along the x-axis now as a jet that is going along the z-axis. And all the equation of motions are covariant with respect to orthogonal transformation. And something like that happens also in quantum mechanics. You can perform a unitary transformation, that is the complex, the generalization to the complex space of orthogonal transformation. So it's a transformation that preserves the norms in the complex Hilbert space, and you can take your wave function and change it and, say, rotate it with a unitary transformation, and you have really not changed the physics of your problem. You're just looking at your wave function in a transformed framework. And here I'm showing an example of a unitary transformation. This is a transformation in which I take my vector. Now my wave function, you know, can be thought as a vector in Hilbert space. So I take my vector psi mk, and I perform a unitary transformation that's a bit odd in the sense that is continuous. You see, I'm integrating over the Brillouin zone, and I'm multiplying psi by these phase factors e to the minus ik dot r, where capital R is a reciprocal lattice. Okay, so this is also a unitary transformation. It's just a continuous unitary transformation. To make it simple, you could discretize that sum in the Brillouin zone, and then if you discretize over 100 points, it's just a transformation that involves a 100 by 100 matrix. And this is a transformation that was defined by Gregory Wannier in 1937, and to be honest, it looks a lot like a Fourier transform. And the result of that transformation is what we call a Wannier function, and is an object for which we'll describe properties and characteristics. But the first important statement is that this transformation is not uniquely defined. For a very simple reason, because psi and k, the eigenstates of the Hamiltonian, are not uniquely defined. Actually, if psi and k is an eigenstate of your Hamiltonian, psi and k times a phase factor times e to the I alpha, where alpha is a real number that is just multiplying by a phase, something that has norm 1, is still an eigenstate of the Schrödinger equation. So the Schrödinger equation does not decide the phase of your wave function. That means that in your transformation above, you could actually think that there is what we call a gauge freedom. That is, if we have calculated psi and k as a function of n and as a function of k with our favorite electronic structure code, and we are performing this Wannier transformation, we still have the freedom for any k that, remember, is a continuous variable, to multiply it by an arbitrary phase factor that I've just written as e to the I phi n of k. Okay, and that arbitrariness is actually important because that phase factor depends on k, so it changes the result of the integral. So that Wannier function that I've symbolically labeled R of n, that object that is some complex wave function defined in real space, actually is not uniquely defined in the Wannier transformation. It depends on the phi of n, and actually I have the freedom of choosing the phi of n of k as I want, that can give me some desirable properties to the Wannier function. So in this transformation there are properties, and I'll come to those in a moment, that are completely defined by the shape of the transformation, but then there are other properties that depend instead by my specific choice of the phase factor e to the I phi n of k. And the situation in terms of gauge freedom is actually worse or larger than that, and I'll comment in a moment. But first, I want to give you a very coarse feeling of the fact that this Wannier function R of n should actually be localized. That is, it should decay to 0 as you go very far away in space. And I've rewritten here this Wannier transformation in the specific case in which the capital R of the previous slide, if I go, in the Wannier transformation, there is a e to the minus ik dot r, where r is a direct lattice vector. I choose that direct lattice vector to be 0, so that phase factor is 1, and the Wannier transformation is nothing else than the integral of psi and k in dk, and I'm just for a moment thinking at a one-band system, so there is no band index. So the first formula there writes explicitly the Wannier transformation for the specific case in which the capital R lattice vector is 0. And I'm actually using the fact that psi k can be written through Bloch theorem as uk times e to the ik dot r, where r now is a lowercase r. So r is the point in space that is also an argument of u of k and is an argument of my Wannier function v of 0. Okay, I want to understand what that Wannier function w of 0 as a function of r looks like when I go towards infinity, when lowercase r becomes very large. And in particular, I look at it not only in the limit of going to infinity, but I just focus on points that are direct lattice vectors. So are these capital R of I that are defined in the second line. So I'm looking at the Wannier function towards infinity, just looking at a direct lattice vector, and the expression in the integral simplifies because the u of k that is now evaluated at a direct lattice vector, because of the periodicity of the u function from Bloch's theorem, is going to be equal to any other direct lattice vector, and in particular is going to be equal to the case of lattice vector 0. So the first term in the integral is uk of 0 times that phase factor e to the ik dot r. And now you see why for ri becoming very large, this term is going to be 0. Very heuristically, this is not at all a demonstration, but basically what I have is that that phase factor e to the ik dot ri, when r is very large in the limit of r of I going to infinity, is going to change as I do the integral. You see, ri is very large, and so even discretize for a moment that integral in k, as I move from 1k to the next, however little I move from 1k to the next, the ri is so large that the product k dot ri can be anything. And so that phase factor basically oscillates wildly. And it really means that in the infinite limit, those wild oscillation means that, you know, the averaging of uk of 0 with wild oscillation will be 0 on average. This is, you know, something that would make a mathematician run away and throw up, but is just, you know, a very general statement of the fact that this wave function should be, in principle, localized. And actually demonstrating that Wannier functions are localized has been one of the difficult problems in solid-state physics. It was first addressed by Walter Kohn in 1959, De Cloiseau later on. Nenciu in Romania did a lot of very important statements, and actually the problem was only solved in 2007. It's a paper to which I also contributed, but it was really the work of Christophe Bruder in Paris, basing himself on a very important theorem on the so-called triviality of block bundles done by a mathematician in Rome whose name is Gianluca Panatti. So the problem of localization in 3 dimensions of Wannier function has only been solved in 2007. So for the time being, I just keep it at the heuristic level. And now I want to conclude this introduction, you know, with the more general gauge freedom, gauge transformation that I have in the case of, let's focus for a moment just on an insulator, and that is the fact that I can also mix at every k point in the Brillouin zone bands between each other before doing a Wannier transform. So here I'm looking at an example in which I have 2 bands, right bands n equal to 1 and then equal to 2, and what I'm introducing is a generalized degree of freedom in which at every k point, and the arrows point to psi1 and psi2 at the zone boundary, I actually decide that I can mix those two Bloch wave function between each other with a unitary transform. And so on the top line here, I have a transformed wave function that I call psi of w that comes from the mixing for a given k point of all the bands that I want to consider. Here are only two bands, so M will sum over 1 and 2, and I mix those two bands with a unitary transformation. That is exactly in a Cartesian representation like saying I have two vectors and I change my representation with a orthogonal transform in case of real space of unitary transform. So black psi1 and psi2 are my original eigenstates, and the unitary matrix is changing them into the red psi1w and psi2w. So this is the most general gauge freedom that I want to have. So my, let's say, generalized Wannier transform, omega tilde, that's just trivial. I'm adding and subtracting the same term, but you can see right away that omega tilde is a positive definite, and that's very easy because it's just the sum of positive terms. And one can demonstrate that omega I is also positive definite. And not only that, but one can show that omega I is what we call gauge invariant. So no matter what the unitary transformations U are that we choose, the value of omega I will not change. So when we maximally localize the Wannier function, we are only changing the contribution omega tilde to the localization functional. And the demonstration that omega I is positive definite and gauge invariant is here. I won't really go into it. I just use a projection operator P and Q. Projection operator P is the projection over all the Wannier function. Q is its complement. And by using those projection operators, I can write omega I as a sum over, again, the four Wannier functions in my unit cell of that expectation value of the position operator R in the different the position operator R in the different X, Y, and Z direction, averaged over the sum, that C means a sum over all the four Wannier function of PRQ. And because that term is a sum of positive contribution, and because the projection operator do not depend on the unitary transformation, the omega I term is gauge invariant. Danusi, you're still hearing me, correct? Okay, very good, very good. So the only thing that remains in all of this is taking into account that calculating position operator and their powers is actually an ill-defined operation. And you see it right away if you, say, want to calculate the position operator on a periodic function. You see that in the limit of that integral going between minus infinity and plus infinity, you can get whatever results you want, depending on how you take. So in general, expectation values of the position operator are ill-defined in periodic boundary conditions. What is interesting is that expectation values of the position operator between localized orbitals, that is, provided the omega 0 is localized, of course that position operator expectation value omega 0 r omega 0 is going to be a well-defined quantity. And if I take omega 0s that are really defined as a Wannier function, as a Wannier transformation. I written it on the first line. It's the simplest Wannier transformation with no unitary matrix, just to simplify the math with the phase factor equal to 1. But if I take the omega 0 as a Wannier transformation of Bloch orbitals, and I use an integration by part, I can prove basically the identity in the square rectangle. That is, the position operator calculated as an expectation value related to a quantity that involves and in particular involves the periodic part of the Bloch wave functions, those u of k that I written there, and it's really the integral over the Billiard zone of what would be called in topology u of k, so that the periodic part of the Bloch orbitals. So without really sort of dwelling too much on the math, what I'm trying to say is that there is a practical way to construct the expectation value of the position operator between Wannier functions. And remember, we need the expectation value of the position operator and the expectation values of R square to minimize our function. And the expectation value of R can be calculated directly from the Bloch wave functions, in particular from the periodic part of the Bloch wave functions. And there is another expression that I haven't written here. It's on the Review of Modern Physics. There is a Blount identity also for the powers of R, and the power of R square is related to the Laplacian with respect to k. Okay, so the bottom line is that in order to minimize our functional, we need to calculate expectation values in reciprocal space of the gradient, and we'll do that by doing a finite difference representation of the gradient. And again, the math here is not terribly interesting, but if you look at the bottom line, I've rewritten again the expectation value of the position operator between two Wannier function as an integral of the Berry connection, and the integral, I've now discretized it, rather than being an integral of the Brillouin zone, is a sum over a regular mesh in the Brillouin zone normalized by the number of k points. And so I need to calculate the gradient with respect of k of u of k, and I'll do that again with a finite difference is the difference. So, and that I can, what I can do is I can sit at a certain point k, and I can look at the k points in my neighbors. So suppose that you are using an FCC lattice. So an FCC lattice in reciprocal space is a BCC lattice. So on a regular mesh of k points in reciprocal space, every point will have 8 neighbors, every k point in your Monko-Spack mesh, and then those little b vectors are going from myself, I am the k point where I want to calculate the gradient, to all my 8 neighbors, and I calculate the gradient by finite differences just by taking the difference between the function at my neighbor minus the function where I am. It needs to be done as a vectorial identity with the proper normalization, but that's just trivial mathematics in that first line, and that's my finite difference approach to calculating gradients. And so basically what becomes apparent from this finite difference representation is that I need to calculate the scalar products between the periodic part of the Bloch wave function at every k point and at every neighboring k point. So this matrix M is, you see that I've just defined, is really at every k point on a regular mesh in reciprocal space gives me the scalar product of the periodic part of the Bloch wave function at that k point for that band, and at a neighboring k point, k plus b, at any other band that I want to calculate. And so this is, if you want, the magical ingredient that my electronic structure codes need to calculate, be it Bn to k, be it PWSCF, be anything else. What I need to M. And if I have, say, gallium arsenide, that will be the M matrix will be a 4 by 4 matrix, because lowercase m and lowercase n can go from 1 to 4, and I will have one of these matrices at every k point, and actually I will have 8 of those matrices at every k point, because I need to calculate at every k point scalar products with the neighbors. And then it's just a matter of using the previous 2 slides and a lot of boring mathematics to show you that if you have calculated these matrix elements, that is, if you have calculated them with the periodic part of the Bloch wave functions that your code has given you, the expectation value of the Wannier function calculated with a unitary matrix U that is just the identity, so without having started to put into Monte without a center of the Wannier function that is just a function, a complex one, as you see, the sum of the imaginary part of the logarithm of this matrix, and it will have a spread that involves, again, the imaginary part of the logarithm of those matrices and the square of the matrices themselves. And this is just very boring math. I don't want to go into that, but what I want to say is that now we have the mathematics and the algorithms to calculate centers of Wannier functions, spread of Wannier functions, and now we can ask ourselves the question, how are these centers and spreads going to change if I start rotating my Bloch wave function, that is, if I start rotating my periodic parts U of M, so that if I perform a rotation U, my matrix capital M will go into a U dagger. We are almost done, at least for the math of it. So I'm asking myself, what is the change in the spread of the Wannier function if I make an infinitesimal rotation of the Bloch orbitals? So an infinitesimal rotation, okay, so a unitary matrix, okay, in the limit of a infinitesimal change becomes an antisymmetric matrix, because a unitary matrix can always be written as the exponential of an antisymmetric matrix, and so in the limit of that antisymmetric matrix being small, the exponential of x becomes just x, and the identity is not interesting. And so what I'm asking myself is, what is the change in the functional omega if I perform an infinitesimal rotation of the orbitals? And so the omega over the W, where W is antisymmetric, is the change in the functional. So it's the gradient in the functional with respect to localization. And that gradient is, again, a very complex mathematical quantity that at the end depends only on the capital M matrix elements. So not only I'm able to write the position of the Wannier function centers and their spreads, but also how those spreads, how the localization functional omega is going to change if I perform an arbitrary infinitesimal rotation. And so then I can use steepest descent or conjugate gradient algorithm to move in the direction of the gradient and keep rotating the orbitals until I've reached the minimum of the localization functional omega. Okay, this ends the math part. Are there any questions? Okay, so now becomes the, comes out the interesting part of this. That is, what do I obtain if I take this localization procedure? So let's take the valence bands of silicon and let's mix all of them together. At every k point, I mix them with matrices U. I do the integral over k, and when I take them out of my electronic structure code, I will have a huge spread. The localization functional will be huge, but I can take the gradient of that localization functional with respect to a unitary matrix, and so I can define an iterative sequence of small unitary transformation, each of them making the localization functional smaller and smaller and smaller and smaller until my Wannier functions become as localized as possible. That is, they become maximally localized. And what I obtain if I do this in silicon is that I obtain 4 orbitals, as I've shown them here. And each of them really looks exactly as you imagine a covalent bond between 2 silicon atoms. And if instead of doing this in silicon, I do it in gallium arsenide, I obtain something that is very similar, but is just more leaning towards the electronegative anion, more leaning towards the arsenic. And if I still do it in silicon, but not in crystalline silicon, I do it in amorphous silicon, I still obtain Wannier functions that look a lot like covalent bonds, and most of them are regular looking as the 2 on the bottom left, but occasionally there are defects in amorphous silicon where the silicon atoms are not 4-fold coordinated, and the Wannier function immediately recognizes that, and it looks different. It looks like it's coordinating over more than 2 atoms. And if instead of studying a periodic system, I was studying a molecule like the benzene molecule, and I was doing this localization, I would obtain what Foster and Boyes in Cambridge in the 60s had already seen. That is, I would obtain localized molecular orbitals, and the top left, that's benzene, looks like a carbon-hydrogen bond. The top right looks like a carbon-carbon single bond. And then the one on the bottom left is one of the 2 orbitals that contribute to a carbon-carbon double bond. Okay, but the algorithm, I won't do it, but translates automatically into molecular orbitals if instead of having a truly periodic system, I have a single molecule in my unit cell. But the power of this, of course, is not to study molecules, but is to study crystals and to study periodic systems. So these are actually some of the first applications that were done by the group of Michele Parrinello. In particular, on the left, again, is amorphous silicon, where the Wannier function, I don't know if you can see them in the top 2 panels, they can sometimes look exactly like covalent bonds and sometimes look like lone pairs. So the Wannier function technique became very powerful to explore the electronic structure of defected systems, or it was used, and that's the right panel, to study coordination and bonding in a liquid, and in this case in liquid water. It's a bit difficult to see, but in black and gray are the water molecules, and each water molecule has 8 valence electrons, and they are spin unpolarized. So there are going to be 4 Wannier functions, 2 that look like hydrogen-oxygen bonds, and 2 that looks like lone pairs. And looking at the statistics of the distribution of the centers and the spreads in water, has been one of the very first examples where Wannier functions were used to understand the chemical nature of bonding. But these are things that David Vanderbilt will discuss tomorrow. So I want to conclude my talk. Do you understand that we have 5-10 minutes left maximum, Tanusri? Yeah. So, yeah. So I wanted to conclude with the work that we did together with Ivo Sousa in generalizing our problem from the case of semiconductor and insulators to the case of metals. You know, up to now we have discussed silicon, gallium arsenide, water. These are all systems where the valence bands are separated by from the conduction band by a gap. And of course, then there is a gap also between the valence bands and the lower lying core states that would give rise to flat, very separated bands. But the question is, suppose now we are dealing with a metal. I'm doing here the example of copper. And, you know, we have all this mental picture that copper has D-like, 3D-like localized orbitals that give rise to the 5 flat bands in the middle of this figure around the Fermi energy. And then there is a parabolic 4s bands that give a lot the metallic character to the system. So how do we deal in this case with Wannier functions? Because you see, in this case, as we span the Brillouin zone, sometimes it's clear, if you can see my arrow here, you see around gamma here, can you see the arrow? No, I'm showing copper. What are you seeing? Oh. No, let's see. So it's not appearing. Do you have a disentanglement slide now? Okay, great. So this is copper, sorry. So you see, I was talking about these 5 flat bands in the middle of the picture and the parabolic 4s band. And the question, yeah. Okay, let me try to unshare and share it again. Can you guys see me now? Hello? Does it work now? Okay. Okay. So what I was going to say is that now, you know, those unitary matrices that for silicon and gallium arsenide were 4 by 4, now it's not clear what they should be, because there are places in the middle of the, say here, I don't know if you see the arrow, where it's very clear what the 5 3D bands are, but there are other regions around here where I don't have 5 bands, I really have 6 bands mixed together, or even 7 bands mixed together. So it's not clear how I can extract from this spaghetti a manifold of dimension 5 that then I can operate with the maximal localization strategy. So the work of Ivo and myself and David on disentanglement is the additional step that is required for the case of metals on how to separate out of the spaghetti on the left a manifold of dimension 5 on the right that is smooth out of which I can do my usual localization trick and obtain Wannier function that in this case look like 3D orbitals. So what I'll comment in the next slides is how to go from the left panel to the center panel, how to disentangle one group of bands from another group of bands. And I'll use another criterion. While before we have used the criterion of maximal localization to do a transformation to make Wannier function as meaningful as possible, here we introduce a different criterion that is the one of maximal smoothness or optimal smoothness that I'll describe better in a moment as a criterion to disentangle one manifold from the other. And intuitively, that criterion of maximal smoothness that we use to extract a manifold of dimension 5 is the criterion that says that in the panel of dimension 5, this manifold here has been obtained from the spaghetti by asking that the 5-dimensional manifold at a certain point k in the Brillouin zone changes as little as possible as we travel around the Brillouin zone. So the criterion of disentanglement is a criterion of smoothness that says we are going to disentangle a manifold of a certain dimension. In this case, it's going to be dimension 5, and we are going to find out how to disentanglement by taking linear combination of whatever bands I have on the left panel that could be typically 6, 7, or 8. I'm going to take linear combinations of those such that the best 5 that I obtain give rise to a manifold that changes as little as possible as I move around the Brillouin zone, so it maintains as much as possible its character. You can think at this, a simple example would be if you had only 2 bands crossing, okay? So how do you know after the crossing if you are still on your original band or you have changed bands? Well, you calculate scalar products between, the wave function after the crossing and before the crossing. If the scalar product is very large, you're really following the same band. If it's very small, you have probably switched bands. So you're using scalar products to understand the character of your system as you move around. And the mathematics of this is this. Basically, we defined S as a linear combination of whatever. We start with 8, 9, 10 bands, and we mix them all together, and we obtain a manifold of dimension 5 that is my target. So 8, 9, 10 is my input, 5 is my target. I mix them together, and these matrices are not unitary anymore, but the manifold of dimension 5 that I obtain at a certain k point needs to be as smooth as possible, and it means a smoothness that is scalar product with the manifold that I have obtained at a neighboring k point is as large as possible. That is, I've maximized the overlap. So the net result, how do I obtain that smooth 5-dimensional manifold? I maximize the smoothness. That is, I defined it to be such that the manifold at a k point, the manifold at the next k point have a maximal overlap. And how to do that is again somehow mathematically complex, but has to do with taking the highest eigenvectors of the projector operator P on the subspace that I want. And so if we do this, we have a recipe to separate bands. And this is an example, say that the top panel is again silicon, and I've plotted the 4 valence bands, and you know already that those 4 valence bands that are a group of what we call composite bands separated by a gap. If I mix them all together, I get the bonding orbital that I've shown. But now what I can do is I can also extract or disentangle a manifold of dimension 4 from the conduction band, that now it's all spaghetti. But I extract a manifold of dimension 4 with this disentanglement procedure, and what I get is the antibonding orbital that I plot in gray that looks a lot like a chemical antibonding orbital. Or what I could do is, rather than separately transforming the valence bands and disentangling 4 conduction bands and localizing them, I could say, well, let's try to mix everything together. Let's mix the 4 valence and let's mix the bottom of the 4 conduction. And if I mix those 8 orbitals together, what I get are 8 localized Wannier function, 4 sitting on one silicon, 4 sitting on the other silicon, and they look exactly like sp3 orbitals. So I've done really the inverse tight binding. I've started from the exact band structure, and I've constructed sorry. And I've constructed in the bottom panel mathematically the sp3 orbitals that give rise to that band structure. So I've inverted the tight binding procedure. I've done a plane wave calculation, and I've obtained the orbitals that give rise to that band structure that I want. This was for the case of silicon. I have other examples. As I said, I can obtain the band structure of copper, the D bands of copper. And, one important comment here is that my physical sense tells me that I want to disentangle a manifold of dimension 5 that are the 5D orbitals. But then I need to make a computational assumption, that is, I want to ask myself, what are the states that I use, that I try to mix to obtain that manifold. And here I have 2 examples in the top and in the bottom panel. In the top panel, I use states in the window that goes up to 0, the dashed line. So I take all the states below the dashed line and I mix them all together. Or in the bottom panel, I actually enlarge my freedom. I take all states that are in the panel. So I use a large window to mix things together. And you see, when I use a larger window, I get a slightly flatter subspace because I have more variational freedom, so I can make my manifold even smoother. But if you want, I make it less physical, and in fact, it represents the bands less well. In principle, if I had increased the window more and more and more, taking more and more of the conduction states, I can make my red manifold completely flat, because now I'm mixing a lot of things with the only criterion of smoothness. And so the physical result is a combination of this criterion of smoothness, but then taking states that sit in a window that captures all the physics you care about, that is the 3D physics, but not more than that. And that is the sort of difficult part of the Wannier functions. And the last 2 slides I'll skip are just other examples in which we find maybe just one orbital that describes the parabolic band of copper, or a hybrid orbital that describes the bottom of the band structure of copper. And this is the last slide for today. I'm just comparing, the band structure that we obtain in red from this disentanglement procedure and the band structure that you would have obtained by constructing Wannier functions just by projection techniques. And as you see, very often the projection technique is actually very good, but is much more jagged in other parts of the Brillouin zone, because again, it's not trying to provide a maximum smoothness, if you want, as we go around the Brillouin zone. Okay, I think I'll stop here. I have to apologize, as it always happens when you do things in remote. I've been much slower than I thought, and I haven't given you the part on constructing model Hamiltonians from Wannier function and using it for ballistic transport. But you have the slides, and I'll discuss with David if he has the time or wants to show. So I think I'll conclude here, and I'll ask Tanusri if there are questions left. Yep. So this is an old calculation. It was done with a unit cell, I believe, of 54 atoms. Although the details are in the 2001 paper. You typically would do ab-initio molecular dynamics at high temperature, where silicon is liquid, then cool it down, but slowly enough, and it's a very difficult problem how to get a meaningful structure, a very long simulation in which you melt the silicon and then you cool it down slowly. Or sometimes they use much shorter simulation like ab-initio molecular dynamics, but then they do some Monte Carlo steps in which they try switching atoms that are very poorly coordinated to see if slowly you can reach a more meaningful four-fold coordinated amorphous configuration. But the issue on how to obtain a meaningful structure of an amorphous crystal is in itself a very complex problem, and for which there isn't a single satisfactory solution. Can you hear me?
I have one question. Why do we bother about the inverse problem? We already have the band and the delocalized wave functions. Why do we want to get the localized wave? Localized wave functions.
Tanusri, you have to repeat it. For three main reasons. Can you hear me? Can you hear me? Can you hear me? Okay, there are three reasons. One is because in a localized picture, things becomes transferable, and so you can construct model Hamiltonians. So, I had examples on functionalized carbon nanotubes where, in a localized picture, I can build the Wannier function of a perfect carbon atom in a nanotube or a carbon atom with a covalent ligand. And if you want, I have my Hamiltonian now in a localized basis that is extremely sparse. And so I can now solve the electronic structure of enormous systems with ab-initio accuracy, while I wouldn't be able to study a system with, 10,000 or 100,000 atoms directly with an ab-initio calculation. I can actually do this using the Wannier representation. So that's one example, to study model Hamiltonian, either to study large systems or to do correlated electrons techniques. That's what the dynamical mean field theory community that you'll see does with these Wannier functions. So this is one goal. The second goal is to understand the chemistry of your system, because now your Wannier functions look like chemical bonds. You can study the nature of chemical bonds using these Wannier functions. And the third one that David will also mention tomorrow has to do with the modern theory of polarization. There are theorems that relate the electrostatic properties of the Wannier functions to the electrostatic properties of the solid described quantum mechanically. And so that's the third major reason.
So there was a small comment on how you can distinguish between two bands by computing some scalar products. So I didn't understand that. So if Nicola can expand on that.
Yeah. Part of it. Yeah. 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 So suppose you have only two bands, and suppose, or maybe let's suppose that you have three bands, and they are all fairly flat and close to each other. But somehow you want to separate one from the other two. So how do you do that? Well, you have different possibilities at every K point of taking linear combination of these three bands, or let's say linear combination of these three bands. And if you want to separate these three bands into a one band and two bands, your sort of objective would be to have as small as possible a scalar product between band A and the combination of band B and band C. So at every K point you have three bands, you can mix them all together, but how do you separate them in two groups? You use a scalar products. So you want to be one band to be as different as possible from the other two. So in general, sort of, scalar products tell you how similar you are with your neighbors. So suppose that you are in a crowd and you look at your neighbors, and the scalar product with your neighbor is going to be largest. The more similar your neighbors is going to be to you. Same height, same weight, male, female, long hair, short hair, all these things. And so scalar products between wave function really are large when the wave functions are very similar, are small when the wave functions are very different. So they can be used to say follow one band. If I have, if I go to the example of the 4s band in copper, how do I follow that band when it starts getting spaghetti-like mixed with the 3D band? Well, I have to look and mix up things and pick up from that mix the object that is as similar as possible to the 4s band at the previous K point, and as similar as possible to the 4s band at the next K point. And when I make this into a global property that, this band is as similar as possible over all the Brillouin zone, I have a sort of magical way to connect pieces where the 4s band is uniquely defined, pieces where the 4s band is uniquely defined somewhere else, and extract in the middle the right combination of the states.
Also in the Bloch theory, at a given K, two different n states have to be orthonormal because they come from the solution of the same Schrodinger equation kind of thing. but two states of different k in the same band need not be orthogonal. The symmetric part, sorry, the periodic part of the wave function. If I include the e to the power I kr, all of them will be orthogonal. But in the same band, if I no, I'm just adding to the answer.
Okay, I let the discussion go offline. I picked up only a part of the questions. So let me just mention that now we are not doing any more unitary transformation. So we are picking up different pieces from different bands using non-unitary matrices. And maybe I could sort of, the paper by Ivo Sousa described that in more detail about these issues of orthonormality or not. Okay, so thanks a lot. I hope this was, reasonable, and I'm very sorry about all these troubles in doing this in remote. Yeah. No, that's good. Great pleasure. Thanks a lot. Okay, bye everyone, and best luck for your workshop.